well in your first sessional? First, only one batch has got the papers. 2 batches. Among the 2 batches, how many have done well? Huh? Passing marks. What passing marks? Huh? Out of 50, right? So what is your passing marks? 25. I don't want that passing marks. Huh? Tell me who have really done well, who have feel confident that yes, I have done well. My sessionals went well. Not really, no? Not really. Yes. Huh? I too felt so. Well, I did the evaluation. Not really, but it's not bad also. Okay? To what the batches, what we used to see earlier, for the last 2 or 3 years after the NEET has taken, I really see a drastic improvement. I mean, students are you all are really good. Only thing is, not when I say all, I just mean a generalized term, but there is, I think, one person who got 0 also. Huh? I don't know who it is. I didn't bother to see the name or anything, but this is there. I cannot blame the group, but there were few answers were written excellent, excellent. So I think your main question has been corrected by one of the junior teacher, where I saw you been given what you call, you would have deserved a little more. That's all I would say. So don't go. So don't, no, I cannot do anything. I'm just telling you, valuation, only senior teachers. Let me complete. While it comes for your final valuation, university only gives the senior teachers to evaluate. Okay, university has its rule. It does not give the junior teachers to evaluate. With your experience of 5 or 6 years only, they get it. So I think you will do. Don't worry about that. But I have seen most of the main question was a little undervaluated. We as seniors, we feel, okay, this much student has written is really good. And I give 9, 10 also when the answer is really good. Yes, I do give. I don't squeeze myself for 6 and 7. Okay, so this is all I want to tell you is, don't worry if you have come a little less from 4 or 5 marks. Don't worry, don't lose your heart. You can do better next time. Okay? Yeah, with that we go to the topic. I want to finish up. Students, enough. But some of you who have not studied, please study. There is, now the new rule has come. Within today, I think we have to send the marks to the university. So this is something new. I was telling you in my first class, there is a lot of things, lot of manipulation, lot of things happening. Everybody scoring 18, 19, which is not okay for my point of view for the good students who do hard work. So today the university has come this year with the new rule. By 5th, I think we have to upload all your internal marks. So now no more giving the marks, taking the marks will happen. So it's all your efforts when it comes to your sessional marks. Okay? And also there's an university rule. You are supposed to get 10 on 20 to be eligible. I hope you all know that. To be eligible. Otherwise you are not eligible even to write your final exams. Not aware of that? Yes. You are supposed to have 7 on 20 to be eligible. So there is a one branch. What you are not, suppose you are not aware of it. Last year I think 20 students were kept back because there was no sessional marks. The whole 150 never goes for exam. Always it will be 130 who go for exam. 20 are kept back, either for attendance or for the marks. So please be aware, please do your sessionals well. 7 is not a big marks, but definitely it is difficult. I'm not saying it is very easy. 7 on 20 is not easy. Okay. Now we go to the topic. Let us go with students. Now it is enough. Yes. If you are not aware, good, very nice. I could give you some information. I thought this has all been told to you because this is very, very important. Because your first sessionals was the easiest sessionals you could score marks. Second is not going to be easy. Third is absolutely not going to be easy. Because what they have done is, third sessionals, they have kept the whole portion. And that too, third, you have genetics, which is so vast. plus they are keeping the whole portion, so it's not easy task for you. So don't hope anything on third, please hope on second. Make up something for second. I think best 2 they take. It's taken as S2. So at least if you're not done first, second you do well, and third depends. Third, as I told you, keep from yourself, from beginning itself, study the earlier portion also, because they keep the whole portion for third sessionals. Let's move to, now you have done with lipids, almost 2/3 is over. I just have a small part that is 1/3 of lipids to be done. So I don't know how it has gone with metabolism. Lipids metabolism is a little tough. Okay, I'm not saying it's very easy, and it's not that it's tough also, but you have to put your efforts. So let's move today to cholesterol metabolism. Cholesterol metabolism. This is a very, very important main question been asked in your exams, quite frequently asked, cholesterol metabolism. Now when we say of cholesterol, you have finished your chemistry. I had asked 2 or 3 people in the viva, what is the ring structure present in cholesterol? Cyclopentano, perhydrophenanthrene ring. See the voice. Yes, this is what happened. I never got the answer for my question in viva. So the ring structure that is present in cholesterol is, I will not draw the structure now because at the end I will draw. The ring structure that is present is cyclopentano perhydrophenanthrene ring, because there are 4 rings. Okay, there is a cyclohexane ring, free cyclohexane ring, and 1 pentane ring, and 1 perhydro group. So they belong to the phenanthrene ring system. So that's why it's called as, again I repeat, cyclopentano perhydrophenanthrene ring system. Cyclopentano perhydrophenanthrene ring system. Okay, so this cholesterol, almost about 1 gram of cholesterol is synthesized in the body every day. Okay, so it depends. Basically the diet and regulation is really there. We'll learn about the regulation. So how much you take diet, also the de novo synthesis of cholesterol. Now where is this cholesterol synthesized? Cholesterol is basically synthesized in almost all the tissues, like 50% is in the liver, 15% you have in the intestine, and you have a little more amount here and there in, we have it in the reproductive organs, okay, adrenal cortex, reproductive organs like in ovary, testis, placenta, and adrenal cortex, yes, it's very important for the steroid hormones to be produced, and also we have it, as I said, in the skin also. So basically almost everywhere it is there. The most important tissues are, so as you know, when you write your metabolism at the cellular level and the subcellular level always. So liver, you have skin, intestine, adrenal cortex, and the reproductive tissues. What is the where is the subcellular level? Subcellular level, this is synthesized in the cytosol and endoplasmic reticulum. Cytosol and in the endoplasmic reticulum. Okay. Now cholesterol, let me, at the end when I have time, let me go with the functions, and let me start with the metabolism because it's a little long metabolism. Let me try to finish it up. So to start with, the starting material that we have for the cholesterol synthesis is acetyl-CoA. So the acetyl-CoA is the starting material for the cholesterol synthesis. Now acetyl-CoA you are quite familiar with. You have come across in the fatty acid synthesis over there. You have seen from the citrate lyase reaction, isn't it? So acetyl-CoA is the precursor molecule for cholesterol synthesis. And along with this, you have the reducing equivalents, that is NADPH. Remember, always for these reductive reactions, it is NAD, it is not NAD, it is NADPH. Okay, it is not NADP, it is, it is not NAD, it is NADPH and NADPH, which gets oxidized to NADP. Okay, so this is NADPH. It's not NAD to NADH. So this is always to be remembered. The reductive, this as you know, you get it from which pathway? NADPH from the pentose phosphate pathway or from the HM-Shunt pathway. Okay. So the starting material, as I said, yes, it is the acetyl-CoA. Now acetyl-CoA, you have two molecules of acetyl-CoA, in the presence of an enzyme that is called as thiolase. So this initial two reactions will be almost similar like the ketone body synthesis. But what's the difference is ketone body synthesis takes place in the mitochondria, and cholesterol takes place in the cytosol. So it has its own pool over here, one in the cytosol, so you can call them as isoenzymes. You can call them further as isoenzymes. Okay? So the two molecules of acetyl-CoA in the presence of an enzyme that is thiolase, you have, as you already know, what is the product that is formed in presence of thiolase, two molecules of acetyl-CoA? Oh, aceto-acetyl-CoA. Aceto-acetyl-CoA. Okay? Two molecules of acetyl-CoA in the presence of an enzyme, thiolase, will give rise to aceto-acetyl-CoA. Aceto-acetyl-CoA in the presence of an enzyme called as HMG-CoA synthase. HMG-CoA synthase, it forms a compound with another molecule of acetyl-CoA. First step you have one CoA released. Okay. So aceto-acetyl-CoA combines with another molecule of acetyl-CoA, and forms a compound. What is already you know, because the enzyme itself is HMG-CoA synthase. So this CH3 goes up and you have one OH, and this new joins over there. You have CH2 and you have something like this. Okay, aceto-acetyl-CoA combines with another molecule of acetyl-CoA. As you know, you don't have to write these structures, but I want to teach you. For me, it becomes easy. Okay, so it forms a compound what is called as HMG-CoA. Now, what's the full form of HMG-CoA? Beta hydroxy beta methyl gluteryl CoA. Okay, the full form of HMG is beta hydroxy. You can see the group there, beta hydroxy beta methyl gluteryl CoA. So HMG is beta hydroxy beta methyl gluteryl CoA. So it gives forms to a compound called as HMG-CoA in the presence of an enzyme that is HMG-CoA synthase. So till here, as you know, HMG-CoA is produced in mitochondria, which is utilized for ketone body synthesis. HMG-CoA, which is synthesized in the cytosol, is utilized for cholesterol synthesis. Now comes the rate limiting step. We have the rate limiting step, what is called as HMG-CoA reductase. HMG-CoA reductase. You would have heard of this HMG-CoA reductase while I spoke of enzymes. I did tell you So this is a rate limiting enzyme. What are the drugs which are acting, inhibiting this enzyme? Statin, yes, lovastatins. Statins are one of the very important medical treatment that we can give to reduce the cholesterol synthesis in hypercholesterolemia. You can literally see every patient who has got a cardiac problem, they are put on statins. But you have to remember that statins cause a very severe muscular cramps. So they take it continuously, they can land up with severe muscular cramps where CPK can sometimes be very high. So you have to give them a break for some time in between and then continue always again. So that's one of the side effects of statins. So you have HMG-CoA reductase, where, as I told you, it's almost using about 16 NADPH. It is using almost 16 NADPH, and it also uses about ATPs, which is almost about 36 ATPs. Yes, you can imagine the cholesterol synthesis going to be too large, so lengthy, which is going to use. So we have the first NADPH being used here. So NADPH plus H, which gets oxidized to form NADP. And yes, 2 NADPH is used here. 2 NADPH is used here. And when it is using an NADPH, it forms a very important compound. We have it written something like this now. Okay, so CH3, OH comes here, CH2, this one, OOC, carbon dioxide, and then we have, this is what happens. This gets reduced. This gets reduced and forms a very important group, that is CH2. That is why, because as you know, lipids are basically, you have this CH2 groups. So CH2, what happens? The CoA comes out, and it forms something like this. So this is a product where it gets the first reduction that happens, and you have the enzyme which is called as rate limiting enzyme. So the rate limiting enzyme in cholesterol synthesis is HMG-CoA reductase, and this important compound is called as mevalonate. So you can come to a very important step now here from HMG-CoA reductase, where the reduction happens in the presence of NADPH, and it forms a very important compound called as mevalonate. Okay? So I repeat the 4 steps again once more. 2 molecules of acetyl-CoA in the presence of thiolase give rise to form acetoacetyl-CoA. Acetoacetyl-CoA in the presence of another molecule of acetyl-CoA, which gives rise to form HMG-CoA. HMG-CoA in the presence of an enzyme HMG-CoA reductase, which undergoes reduction with the presence of NADPH to form a very important compound, what is called as mevalonate. Okay, clear? So the first step, we can put it across in 4 steps. So the first step, we can call it as synthesis of mevalonate. So from the starting material to mevalonate being synthesized. Okay. Now comes the next step. What happens? So this mevalonate, I never like my teachers writing too much on the blackboard. Huh? We feel like, what is she writing? Where is she going from here to there? Huh? So I like to keep it minimal, but sometimes in our biochemistry, we have to go on writing, it looks like. So that's why maybe my teachers also is to write like that, especially the senior teachers, yes. So, okay, so we keep at mevalonate. Now what happens at mevalonate is, comes your ATP. As I told you, 16 NADPH is used, 36 ATPs are used. Yes. Now comes the first ATP, where in the presence of an enzyme, what may be the enzyme name? Mevalonate kinase. Very good. So you know that whenever ATPs are there, we call it as kinase. So mevalonate, in the presence of an enzyme, mevalonate kinase uses an ATP, where the ATP gets converted into ADP, and what happens is, the fifth carbon, okay, the fifth carbon, that is, we have over here 1, 2, 3, 4, 5. The fifth carbon gets phosphorylated. The fifth carbon gets phosphorylated, and it forms a compound, what is called as, we can call it as 5-phosphomevalonate. The fifth carbon gets phosphorylated in the presence of ATP and forms a compound called as 5-phosphomevalonate. 5-phosphomevalonate. 5-phosphomevalonate, further in the presence of ATP, definitely magnesium is required, further gets phosphorylated. And where does it happen is, and it forms one more phosphorylated again at the fifth carbon. Again gets phosphorylated at the fifth carbon. What do you call that product as? 5-pyrophosphomevalonate. Okay? Some books also say it as diphosphate, but we have always been calling it as pyrophosphate. So I don't know your books, whatever says. Okay. So 5-pyrophosphomevalonate. So 2 ATP is done. One more ATP, again it utilizes another ATP and phosphorylates once again, and this time it phosphorylates over the phosphorylates at the third carbon. It phosphorylates at the third carbon, and it phosphorylates at the third carbon, and it called as 3-phospho 5-pyrophosphomevalonate. Okay. So it is phosphorylated at the third carbon, and it forms a compound called as 3-phospho 5-pyrophosphomevalonate. So to be easy, it just means that mevalonate gets phosphorylated 3 times in the presence of an enzyme. Later enzymes, you can call it as pyrophosphomevalonate kinase. Pyrophosphomevalonate kinase. So basically in the presence of an enzyme called as mevalonate kinase, to form a compound called as, what's a compound? 3 phospho 5-pyro-phosphomevalonate. Okay? So this is basically, it forms a compound there, what is called as 3-phospho 5-pyro-phosphomevalonate. So at the end, we have something like this. Now, why you all are discussing? Is it important? Students, I don't like this. In between the class, don't show your smartness. Not required. Just listen to me quietly. If you feel that you know it, you just ignore. Sit and dream over there. That is better. If you feel it is easy, you can understand. You can go back and read. Books are always there. Teachers are not required. Teachers are not very essential. No problem. You can go back always and read your books. So we have a compound here, what is called as 3-phospho 5-pyro-phosphomevalonate. What is the next step? Next step now, what happens is, in the presence of an enzyme, what we call it as decarboxylase. Call it an enzyme called as decarboxylase. If you want, books name it as pyrophosphomevalonate decarboxylase. That is also okay. Or simply, if you want to write decarboxylase is also okay. So 5-pyrophosphomevalonate decarboxylase, as you know, decarboxylase means removal of the carbon dioxide. So where is the carbon dioxide? Yes, at the very end here you can see there is a carbon dioxide. So carbon dioxide is removed. Along with carbon dioxide, this phosphate is also removed. Along with carbon dioxide, this phosphate is also removed. So phosphate also comes out, okay, and it forms a compound which looks something like this. So you have a compound. So here you have a double bond because this goes off, and you have a compound which looks something like this. So 3-phospho 5-pyrophosphomevalonate in the presence of an enzyme, decarboxylase, removal of the carbon dioxide along with the phosphate that is present in the third carbon. It gives rise to one of the very important compound, and this is the second step. What we call this compound as isopentenyl pyrophosphate. Isopentenyl names are all like this now in cholesterol synthesis. That's why I'm going on repeating. Maybe if I repeat 5 to 6 times, it will enter your head and be there permanently. Okay? Yeah. Isopentenyl pyrophosphate. Isopentenyl pyrophosphate. Now, pentenyl means to say it's an isoprenoid unit which is having 5 carbon. 1, 2, 3, 4, 5. It has got 5 carbon. It is isoprenoid unit. I think you know what isoprenoid unit. Yes, it's a 5 carbon isoprenoid unit. So the first step was formation of mevalonate. Second step is formation of isoprenoid unit. Now what is the isoprenoid unit here? It is isopentenyl pyrophosphate. Now what is the need for it to synthesize a isoprenoid unit? What is the need for it to synthesize an isoprenoid unit? Very easy to think over is, as you know, cholesterol is almost 27 carbon molecule. 27 carbon molecule. Okay? So hold it roughly as 30 carbon. 27, let's approximate it closer to 30 carbon. Now when you say 30 carbon, it's always easy when you have multiples of 5. When you have multiples of 5. Understand this? So it becomes very easy now for you to come to the cholesterol, to reach to the cholesterol point. The first isoprenoid unit that you have is 5 carbon. So how many more isoprenoid you may want to join like this? 5 you will be short. 6, okay, as you mean to say, okay, some many more, okay. So we want, overall, we want 6 isoprenoid units. 6 isoprenoid, so 1 we already have, we want to join another 5 more to it, right. So this is how the synthesis will start from here, once you reach the point of isoprenoid unit. So what's the first isoprenoid unit that you have got? Isopentenyl pyrophosphate. Isopentenyl pyrophosphate. Now what happens to this isopentenyl pyrophosphate? Isopentenyl pyrophosphate, in the presence of an enzyme called as isomerase, isopentenyl pyrophosphate, which is 5 carbon, in the presence of an enzyme called as isopentenyl isomerase, it undergoes isomerization. Once it undergoes isomerization, what happens is it forms a compound, what is called as just shift of the double bond. Shift of the double bond. So what happens is it shifts the double bond over here. It shifts the double bond and it forms a compound something like this. It forms a compound something like this. And this is a second isoprenoid unit, and we can call this as, because there are 2 methyl groups, so what do you think it can be called? Dimethyl allyl pyrophosphate. Okay, so the second isoprenoid unit, again it is 5 carbon. So the first isoprenoid unit was isopentenyl pyrophosphate. Isopentenyl pyrophosphate underwent isomerization and it changed into another compound called as dimethyl allyl pyrophosphate. Dimethyl allyl pyrophosphate. Okay, now what happened is you have got 5 plus 5. 5 plus 5, right? So we add them up together. We add the 5 plus 5 together. Okay. So let's add 5 plus 5 together. So it looks something like this. Sorry, here the double bond doesn't come, CH, CH2, and then you have the CH2, you add up. Okay. Now you have added up both of them together. You have added up 5 plus 5 units together. One isoprenoid unit, that is isopentenyl pyrophosphate, plus dimethyl allyl pyrophosphate in the presence of an enzyme what is called as cis-prenyl transferase. the enzyme is called as cis-prenyl transferase. Okay, cis-prenyl transferase, and forms a compound what is called as, it forms a compound geranyl pyrophosphate. It forms a next compound, that is isoprenoid unit, geranyl pyrophosphate. Okay, so isopentenyl pyrophosphate combines with dimethyl allyl pyrophosphate and forms a isoprenoid unit called as geranyl pyrophosphate. How much unit does this have? 10. Yes. So geranyl is 10 carbon. So now what can we do next to make it 30? What should we do? 3 of this will do. 4 of this. 3 of this we can add, or any other combinations you can think of. Okay. According to me, the combination what came to my mind is, let me add a isopentenyl pyrophosphate. So this is what happens. Okay. So geranyl pyrophosphate is 10 carbon. Let me add another isoprenoid unit, what you first studied, that is isopentenyl pyrophosphate. Let us add isopentenyl pyrophosphate, and we can make a compound almost look like this. Okay. So we have a compound which is almost 15 carbon, which is almost 15 carbon. Okay. So we have almost 15 carbon. So it looks something like this, and this is called as, what is the enzyme here? Same enzyme, cis-prenyl transferase. Cis-prenyl transferase. Please concentrate. Don't take your concentration away. There is still a lot of steps to go. So geranyl pyrophosphate, we add another molecule of isoprenoid, that is isopentenyl pyrophosphate, and made it 15 carbon, and name of this 15 carbon is farnesyl pyrophosphate. Farnesyl, one pyrophosphate will come out because we have 2 there. One pyrophosphate will come out. It forms an isoprenoid unit which is 15 carbon, and it is called as farnesyl pyrophosphate. I repeat the isoprenoid unit again. Isopentenyl pyrophosphate, dimethyl allyl pyrophosphate, geranyl pyrophosphate, and geranyl pyrophosphate and farnesyl pyrophosphate. Farnesyl pyrophosphate is 15 carbon. Okay. Now you tell me what can happen. What's the easy go we can go with this? As simple, yes. Now it becomes simple. 2 molecules of farnesyl pyrophosphate. So let me just add 2 molecules here. Okay, CH2. Okay, 2 molecules. 2 molecules of farnesyl pyrophosphate. That means 15 carbon and 15 carbon will give rise to a molecule what is called as squalene. What is called as squalene. So third step is formation of squalene. So the first step was formation of mevalonate. Second was formation of isoprenoid unit. Third is formation of squalene. Formation of squalene. Okay. Formation of squalene. Okay. Now, squalene, as you can see it looks like a linear chain. It looks like a linear chain. It's basically not a linear chain. It cyclizes. The squalene gets cyclized and it forms almost like a cholesterol chain. Like a cholesterol chain. Okay, I will write the cholesterol. Let me not waste the time with this now. So, the squalene that is present, you can rewrite like a cycle. Rewrite like a cyclic structure. Like a structure that is cholesterol. So, it almost, but the cycle is almost open. The cyclic structure is almost open. Okay. So, the squalene, once you can rewrite like a cycline structure, what happens further to squalene? Now, squalene, in the presence of an enzyme called as hydroxylase and hydroxylase, in the presence of NADPH, so squalene in the presence of an enzyme that is called as hypoxidase. Now, what is the meaning of hypoxidase? Hypoxidase is one atom of oxygen is utilized or is incorporated into this ring. So, if you remember your cholesterol structure, you had seen one OH group on the third carbon. Yes. So, the squalene in the presence of an enzyme called as hypoxidase incorporates one oxygen into squalene. And it forms a compound called as squalene epoxide. And further, with the use of NADPH, where another atom of the oxygen will get reduced to water. So, what happens basically? You have oxygen which can reduce into water, and one atom can be utilized into squalene. Okay? Squalene, one atom of oxygen will be incorporated into squalene to form a compound called as squalene epoxide. And another atom of the oxygen, that is mixed oxidase function, will be used where the NADPH gives the reducing equivalent. So, that can be reduced into water. Okay. So, now it forms a very important compound, what is called as lanosterol. Don't get away fast. So, it's a very important pathway. Just wait. Why you all are so distracted, I have no idea. And all of you look like that. What is the problem? Tired after exams? So, there you have a very important compound, what is called as lanosterol. Now, from this lanosterol, so you have seen from squalene, which was a linear chain, it gets cyclized in the presence of an enzyme, what is called as hypoxidase, and also what is called as cyclase. So, you have to name these three enzymes: hypoxidase, hydroxylase, and cyclase. So, it forms a cyclic structure. Okay, it forms a cyclic structure and gets converted to a compound, what is to a product called as lanosterol. Gets converted to a compound called as lanosterol. So, lanosterol looks something like this. somebody is discussing what is so important. You can't have time. You can't go home and discuss. So the enosterol looks something like this. If you remember your cholesterol structure, I don't know how many of you remember. Let's name it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have 11, 12, 13, 14, 15, 16, 17. We have a methyl group here. We have another methyl group here. Then we have 20. We have another methyl group here, 21. Then we have 22, 23, 24, 25, 26, and 27. So this is how your cholesterol looks with 27 carbon. Now from cholesterol to cholesterol, you have 19 steps to go. From cholesterol to cholesterol, you have 19 steps to go. But since you know it is too much to study another 19 steps, we in our medical curriculum, we have cut it short. We have to study only few, 1 or 2 steps where that is enough. Now how do we do this here? If you look at this, cholesterol, you can find, see, here you have one methyl 2 groups and you have another methyl group at 14 carbons. So at 4, C4 you have 2 and at C14 you have 1 more. So basically cholesterol is how many carbon? 30 carbon. Cholesterol was 30 carbon. Cholesterol is 30 carbon, but the actual cholesterol is about 27 carbon. 27 carbon. Now, what is the difference that you can see here? Okay, one is the ring structure that you are seeing. Second, some important points I will just put you across. On the third carbon, you can see a OH group. Okay, then on the between the 8th and 9th, you can see a double bond. Between the 8th and 9th, you can see a double bond. Between 24 and 25, you can see a double bond. So you can see 2 double bonds between 8 and 9, and between 24 and 25, you can see a double bond. You can see 2 methyl groups at the C4 carbon, and you can see 1 methyl group at C14. Okay? So the first thing that we are doing is cholesterol in the presence of NADPH plus H. Okay? What we are going to do is we have to remove the methyl group. The methyl group gets removed and it forms a compound what is called as zymosterol. Compound called as zymosterol. So 3 carbons that methyl comes out, it comes as HCOH and 2 carbon dioxide. So this is how it is released. 3 methyl groups are out, that is 2 from C4 from here and 1 from here. Okay? You get a compound what is called as zymosterol. Next, zymosterol gets converted to desmosterol. Zymosterol gets converted to desmosterol. How? Desmosterol, this double bond which is there between 8 and 9, it shifts to 5 to 6. So if you see at the actual cholesterol, you have a double bond at between 5 to 6, not at 8 to 9. So the double bond from 8 to 9 shifts to 5 to 6. And that gives rise to a compound, that precursor what is called as desmosterol. Actually, desmosterol is present in the fetal brain. So in adults, it is not there. But only if you sometimes get this gliomas, which are the brain tumors, you get to see desmosterol. Okay? Now, desmosterol further gets converted into cholesterol. What can be the last one that has to be done? Anybody? That one thing, something is there extra in that structure which is not in cholesterol. Yes, the double bond that is present at 24 and 25. Remove the double bond at 24 and 25, and that gives rise to cholesterol. Okay? So from cholesterol to cholesterol, you have done three things. One is you have removed the 3-methyl group, one which was present at 2 which was present at C4, and 1 which is present at C14. Second you have done is you have shifted the double bond from 8 to 9 to 5 to 6. One more thing that you have done is you have removed the double bond between 24 to 25, and that gave you intermediates, zymosterol, desmosterol, and cholesterol. Zymosterol, desmosterol, and cholesterol. Remember, before coming to cholesterol, you have a very important compound, what is called as dehydrocholesterol. Does anybody remember what's the precursor for it? Vitamin D. Vitamin D gets synthesized from dehydrocholesterol. So it's a penultimate compound before cholesterol is formed, that is called as dehydrocholesterol. We will not go to explain because I already told you there are 19 steps. In between I just told you 4 steps are enough. If you know what is the difference between cholesterol to cholesterol. Okay, so this is the synthesis of cholesterol. This is the synthesis of cholesterol. One important point which I just want to make a mention is squalene. We spoke of squalene. Now squalene is a very important compound which gives rise to 2 important compounds today, what is called as CoQ10, that is ubiquinol, and it also gives rise to dolicol. 2 important compounds. Sometimes we ask in Viva for the dolicol, which is present in dolicol. Anybody, where is it present? Dolicol and ubiquinol. Ubiquinol is also called as CoQ10, which is present in electron transport chain. Dolicol is present in the glycoproteins. Dolicol is present in the glycoproteins. Okay, yes students, I'm not going to take attendance, already late. Thank you so much.